Assalamualaikum all. We move to chapter 9 now. It is about optimization. It is a very special variety of equilibrium analysis. Have you heard the terms optimization before? Of course you have heard, although you forgot it already, because you learn optimization when you study business maths or basic maths for business study. Okay, so what is optimizations basically, and what are the things that you need to know in the optimization topic here? Now, so we have optimum values and extreme values. So when we talk about optimization, it is the selection of the best element using certain criteria or conditions from some set of available alternatives. So there are some terms related to this concept. There are four of them: maximization, minimization, objective function, choice variables. So if you see the first and the second one, maximization and minimizations, both of them are basically optimization. So optimization is just a very general term, but if you want to make it more specific, then you may want to talk about maximization only, or you may want to talk about minimization only. Now, objective function and then choice variable. So objective function is the function that we will use to optimize in order to get either maximization or minimization problem. Okay, and a choice variable also known as argument. Okay, now could you think any examples in economic study that deal with optimization? If we want to talk about optimization specifically, let's say maximization, perhaps we want to talk about maximizing profit. Perhaps we also want to talk about maximizing utility, isn't it? And if we want to talk about minimization, maybe you want to talk about minimization of costs, isn't it? Okay, so all of these are basically optimization. You know. So next, when we talk about optimization, we may want to relate it with certain terms also, relative maximum and minimum. And when we talk about relative maximum and minimum, it has to do something with first differentiation. Okay, now in order to check whether we have maximum or minimum, in particular relative maximum or minimum, we must use this test, which is first derivative test. So to make it clearer, let's say we have the objective function given by expression y in equation 1 here, y as a function of x. If you look at expression y here, it is a generic term. We are not given specific function. We are given very generic function. So we don't even know whether it is linear or not linear, whether it is monotonic or non monotonic. So given that it is a general function, so we may have three different possibilities of how it look like. In the form of graph. So for instance, let's say we talk about the first one. Let's say y on the vertical axis and then x on the horizontal axis. Now in this case, which one is the choice variable? Obviously, x is the choice variable that will be used to, let's say, optimize y. If y is, let's say, cost of production, and x, let's say, number of labor. So number of labor here will be used to determine, on how to minimize cost. Okay, now, so let's say we have the first function. The first function may look like this. Okay, so we have point A on the intercept, vertical intercept. We have point B, and then we have point C. Now you look here, for all arguments value, for all x here, okay, the value of y is the same, which is at the horizontal value. Let's say b equal to a, c also equal to a. Let's say a is 5. Okay, so in this case, can you find any choice variable x, whether x is here, here, or here, the value of x, that can give, optimal value of y? Obviously no, because y are all the same. You don't know whether it is maximum or minimum. You don't see whether it is maximum or minimum, isn't it? So all values of choice variables x give a same value of y. Now, Let's move to the second one here. Let's say y is also on the vertical axis and then x is here. Okay, so let's say we start here and then we have something like this. Then you can see that though it is not a straight line, it is increasing. There is no single point shows that it is decreasing, suddenly decreasing before before that it increases and then suddenly decreasing. All of them shows show increasing in nature. So let's say we have point D here. Okay, so if you have within the domain between 0 up to this point, okay, let's say x1 for instance, all are increasing. But if you allow the domain to be moving to the right, then perhaps you can have something like this. So it's still increasing. Okay, so in the second graph here, all right, then we can say that it is monotonically increasing. I mean, the function is monotonically increasing. So can you find any maximum point? Obviously you can't find any maximum point because it keeps increasing like this. Okay, but could you find any minimum point? Now if the domain is given between 0 and also up to this, let's say up to this point only, then you can see D is the minimum point. Okay, so D is the minimum point here, but then, okay, so if we can see here, the minimum value can exist, that is D, if we consider the domain as x or equal to or greater than 0. Otherwise, if we say x can be negative, so perhaps here we can have even lower value of y, isn't it? So we cannot say that D is the minimum point. Okay, now let's move to the third graph. Let's say the same thing. Y is here, and then x is here, and then you start here, and then you have something like this. So you can see here, okay, in this case, if we allow the domain to be between 0 here and up to this x2 for instance, then you can see this point, call it point E, this point, call it point F. Both of them are optimal value, E maximum, F minimum, but within the domain of 0 and x2, isn't it? So here if we constrain the domain, then we can find maximum point at E, we can find minimum point at F. So in this case, they are both of E and F are immediate extremum in the neighborhood given in the graph here. So this is what we call relative extrema. E and F are relative extrema. E is relative maximum, F is relative minimum. Okay, so here, after looking at these three graphs, you can see that there are some terms related to all of these three graphs. Number one is absolute minimum or maximum. Number two is global minimum or maximum. Number three is relative or local extrema. So what we have seen in graph number 3 here, let's say F here, is relative minimum, okay, or local minimum, because it is within the certain specified domain given. Okay, but if the domain is not specified and the domain can be any number between minus infinity to infinity, then you may find that, let's say one point is the maximum, that because you have considered all the arguments or the choice variable within the domain of all choice variable, then that point can be global extrema, okay, global minimum or maximum, or also known as absolute minimum or maximum. So number 1 and number 2 here, absolute and also global are the same thing. Relative is when the point is maximum or minimum, okay, within the immediate neighborhood defined in the graph. Now we also want to look at the first derivative test specifically here. So it's also known as first order derivative. So let's say we have y as a function of x, yeah, so its first derivative will be, f prime x, isn't it? Okay, now, but what is the rule of f prime x here? So basically, it facilitates us in finding the extreme values of equation 1. Like I said earlier, the extreme value of equation 1 can be minimum value or can be maximum value. Let's say we pick one value of choice variable. Let's say x equivalent to xo. Okay, and let's say at xo, there exists relative extremum, could be minimum or maximum point. So if we are at xo and we have maximum or minimum point at xo, then what is the first derivative at that particular point? So let's say we have the first graph here, y and x here, and then let's say we have something like this, okay, and then we have something like this, and then something like this. So obviously we have the first, here maximum point, call it point A, the minimum point, call it point B, isn't it? So these 2 points, A and B, are extreme values, but can we say that f prime x not exists at these 2 points? If you can recall back the lectures that you have done before, that you have heard before, then you can see that f prime xo, let's say xo is here, okay? So at this xo, can we say that f prime xo exists? Obviously no, because this one is a spike, a sharp point. And what about this? Also no. But we know that A and B are extreme values, isn't it? But what if we have something like this? Okay, so let's say something like this. Okay, so we have minimum point here. Let me draw it properly. We have minimum point here. Let's call it point C. And we have another point here. Let's call it point D. Okay, at point C here, let's say XO is here. Then you can see at this point, f prime XO is actually 0, isn't it? Okay, and then here, f prime XO, let's say another XO here. Let's call this one is another XO. It's actually 0 as well. So what can you say here? Here, this is y, this is x. C and D are the, extreme values also, but this time f prime x exists. Okay? In the first graph, f prime x doesn't exist. Okay? So we can see that if we have relative extremum exists, okay, it can be either f prime x naught doesn't exist, like in the first graph. It can also be f prime x naught exists, isn't it? Alright? So here, from these 2 graphs, okay, we are basically looking at the necessary condition for a relative extremum to exist. So it means, okay, can you see here, for a relative extremum to exist in graph number 2, f prime xo, okay, in this case must be 0, isn't it? However, in the first graph, it doesn't exist. Okay, so here, this f prime x not to be exist is just a sufficient, it's just a necessary condition. Okay, it's not a sufficient condition. Here, we have the first derivative test for relative extremum. So, if the first derivative of a function of fx here, okay, at x naught, okay, let's say x naught is here, or here, or somewhere here, okay, then if at this x naught, okay, the function has the f prime x exists for this function at x naught, then the value of function at x naught, will be what? Number one, a relative maximum, okay? If fx changes its sign from positive to negative from the immediate left of point x naught to its immediate right. For instance, look at this point D. On the immediate left here, on this left side, it is upsloping, isn't it? So the sign of f prime x here is actually positive, isn't it? But then once reach maximum here, then f prime x naught is 0 at x naught, isn't it? After that point, point D, then once you immediately move from x naught to another point of x here to the right, then the graph is downsloping. When the graph is downsloping, okay, you know that f prime x is actually negative, isn't it? So negative here. So, so in this case, if to the left of D is positive sign of slope and to the right of D is negative sign of slope, then we know that at point D here, where x naught is here, okay, then here we have what? We have relative maximum. Increase, decrease. So there must be 1 point maximum, isn't it? But then we have relative minimum if f prime x changes its sign from negative to positive from the immediate left of the point x naught to its immediate right. So this point is basically referring to point C. Let's say x naught is here, yeah? Then on the left of C or x naught, you can see f prime x is negative, isn't it? And at C, f prime x naught is 0. And then after that, here, you can see the curve is upsloping. So f prime x is actually positive, isn't it? Okay, but sometimes, okay, you may see, f prime x naught is 0. But to the left of it is, positive sign of slope. To the right of this x naught is positive sign of a slope. Slope also. So, any possibility of this kind of graph? Okay, so for instance, if I try to put it in some small graph at the corner here, so you have this x, y, isn't it? So perhaps you have increasing function like this. So you can see at this point, isn't it? This point, f prime x naught is 0. Let's say x naught is here. But to the left side here, f prime x is positive. To the right here, f prime x is also positive. Can you see how do you know it's positive? Because it keeps increasing. But in the middle here, f prime x naught is 0, flat, isn't it? So here, in this case, we don't have a relative maximum nor relative minimum if f prime x has the same sign on both the immediate left here and immediate right here of point x naught. Okay, so here at x naught we can call it this one, yeah, at x naught here it is a critical value or stationary value, yeah. So it is a stationary value. Why? Because the sign here is the sign of f prime x is 0, stationary, doesn't change, stable. Okay, but to the left of it, the sign is different. To the right of it, the sign is also different. So x naught here becomes a critical value that gives you the change of the sign of slope from left to right. Okay, from positive to negative, like at point C, from negative to positive. Okay, but like I said earlier, it is just a necessary condition. Why? Because you can also have relative extrema at point A in the first graph and also point B in the first graph as well. Let's look at a different graph here. Let's say we have the first one here, y here, sorry, y should be here and x should be here. So let's say the graph looks like this. Okay, so as you can see at this particular point, okay, call this one x naught. you can see if you take this, okay, at this point, f prime x is actually 0, isn't it? You can see the curve before x naught, it is upsloping. After x naught, it is also upsloping. So the range here, if it is upsloping, that means the slope or f prime x is actually positive. After x naught, if it is upsloping, then f prime x here is also positive, isn't it? So can you see the sign of f prime doesn't change after the critical value of x naught? Okay, so if we try to draw all the f prime, curve for the first graph here, this is the second graph. Okay, so you have f prime x, and then you have x here. You can see that at particular value of x naught, then it looks like this. Okay, so can you see here? This is the graph of f prime x, or the marginal graph. This is the graph of total, this is the marginal graph. Okay, when f prime x is equivalent to 0, you see the value 0 is here when x is x naught. Okay, and what happens to the marginal here is that between 0 and x naught, okay, f prime x is, decreasing. After x naught, f prime x is increasing. That means before x naught, the slope or f prime x, the slope of the first curve, or also known as f prime x, is negative. Okay, but the curve of 1 is increasing. That means graph 1 between 0 and x naught is increasing with the slope negative, not negative, but becomes, the slope decreases. On the other hand, after x naught, graph 1 is upsloping and the slope is increasing. Okay, now let's look at the second graph. The second graph here, so let's say we have something like this. At this particular point, we can draw one line that passes through this point. So let's say something like this, right? Okay, now this one is y as a function of x as well, but then we have what here? There's some dirtiness here. Okay, so here, let's call x here as x naught as well. Any value of x before x naught, you can see the curve is increasing. Same goes to any value after x naught, the curve is increasing as well. However, the curvature is not the same. Now, when the curvature is not the same, that means the slope itself is not the same, isn't it? Because it's not a linear line. Now, you can see here, the slope here, although it's not the same, but f prime x is still positive. Here, after x naught, f prime x is still positive. But if we try to draw, the marginal curve or the slope curve in the graph underneath the, the third graph here. This is the third, this is the fourth, yeah? So you have f prime x here and x. Then you can see this is happening. So the graph looks like this. Okay. So if you look here at x naught, if you draw a line, tangent line, it becomes flat. Okay, let me redraw it again. So here, at this maximum point, the tangent line says flat, therefore the slope is 0. Anything below x0, the slope is positive. Anything after x0, f prime x curve is downsloping, isn't it? So can you see the curve before x0 for graph 3 is upsloping, but it is looks like this, isn't it? Okay, and the second one looks like this. So the curvature of graph in 3 leads to the marginal curve that looks like this, increasing and then decreasing. Okay, now, so what we have seen in the previous slides, not only one slide, yeah, we have learned the relative maximum, we have learned the relative minimum, and then if you go back to the previous graph 1, okay, f prime x equals to 0 here when x is x0, you can see that before it and after it, after x0, f prime x is positive. But then you have a flat line here. Okay, so this is not a relative minimum or maximum, isn't it? Because the graph keeps increasing. Same goes to this point. This is not, the point where we have, change in the slope in terms of, the value, because in terms of sign, because the sign is still positive, the curve is increasing, but the slope increase and then decreases, but still positive, isn't it? Okay, so here then there is another thing that we need to know. We call it inflection point. Now, so how to find the relative extremum or extrema for the following? If we only have one point of maximum or minimum, we call it extremum. Okay, extrema is just a plural. So let's do the first one. Let's say f prime x for the first one is actually equivalent to what? Equivalent to 3x squared minus 24x plus 36x, isn't it? And then second step, set it to 0. Okay, what we are doing here is that because we want to find the relative extremum or extrema, we need to do first order condition, get the slope and then equate it to 0. The moment we equate it to 0, then it is called first order condition. Okay, now from here, after setting it equals to 0, okay, then you can find the value of x. So because this is a quadratic function, when you try to find the value of x using factorization, I won't show you the method, but you have to find it yourself because this is just a very high school thing. Okay, so we have 2x, call it x1 equal to 6, and then x2 equals to 2. So these two are basically critical value. Critical values where f of c equal to 0. When f of c equal to 0, when the slope is equal to 0, it could be either, this particular curve could be either at the maximum point or minimum point. So whether at x1 equal to 6 maximum or minimum, or x2 equal to 2 maximum or minimum point, we don't know until we do a certain test. Okay, now at x1, you're going to find fx or y equals to 8. At x2, you're going to find fx equal to y equals to 40. Okay, so here the coordinate will be 6, 8. Here it's going to be 2, 40, isn't it? Whether at this particular point is maximum or minimum, okay, there is a way to check it. Okay, Of course, for the time being, we just look at the, if we look at this graph here, we just want to, whether it is maximum or minimum, we just look at before x naught and after x naught, what happens to the slope? Is it positive or is it negative, isn't it? But actually, formally, there's a way to find it. That method will be explained in the second part here. We're going to learn second and higher derivative. So from here, it helps us to find whether the critical point is a point where we have maximum point or minimum point. So what is second derivative and also what is higher derivatives? So it's actually, if we talk about second derivative, it is actually derivative of the first derivative. So if you have another, you do another higher derivatives, it's a derivative of a derivative. So can you recall back? So we have function like y as a function of x. So if we take y prime, or we can also rewrite it f prime x, then you can see that f prime x is a function of x. So what if we differentiate f prime x, okay, with respect to x once again? Then you're going to get, y double prime or f double prime x, isn't it? So any other symbols for this? If the first one here, you can write it, let's say delta y over delta x. This one then becomes delta 2y delta x 2, isn't it? Okay, so this is another way. But another way here is fx for the first one, the second one here, fxx. Okay, so it means what? When we can find the f double prime here or y double prime, that means the primitive function, which is fx, is twice differentiable. Okay, we know that when we can find the first derivative, that means the primitive function here is continuous. If we can find the second derivative, it is twice continuously differentiable. And the notation can be written as this way or this way. Okay, the function is, continuous, twice continuously differentiable. Okay, so or you put prime here. Can we do the third derivative? What if we differentiate f double prime x here? Okay, so if we differentiate it, then it becomes, f triple prime x, isn't it? But if we differentiate it again, let's say fourth time, so it becomes this. This one is 4. Okay, if we differentiate it for n times, then it becomes fn x, isn't it? Okay, now if you are given this function, try to find the fourth derivative for this function. So it means you have to differentiate it how many times? 4 times. Okay, so this task is very easy. I won't show it here now, but what does it mean if we can get the second derivative? We know that the first derivative, which is this one, yeah, f prime x, it measures the rate of change of, the primitive function here. It is actually the rate of change. But if we have second derivative, it is what? It is actually the derivative of the first derivative, or it is basically measuring the rate of change of the first derivative. Okay, now let's say we have a point, okay, x naught. Okay, so what happens here is you must remember if y as a function of x, this is primitive function, isn't it? Y prime or f prime x, another way to look at it is this one is slope, isn't it? Okay, So for instance, here we want to see what happens here. If we want to calculate the slope at a point where x is x naught, okay? So let's say the first derivative here is positive, okay? Greater than 0. Then what does it mean? Because f prime x naught here is a slope, isn't it? So when it is positive, the slope is positive. When the slope is positive, the curve is increasing, isn't it? When the curve is increasing, then it means the value of the functions tend to increase. Okay? On the other hand, if we get f prime x naught less than 0, it means the slope is negative. When the slope is negative, the value of the functions tend to decrease. Okay? Now, what happens if we take the second derivative? The second derivative, like I said earlier, is the rate of change of the first derivative. Is the rate of change for the slope of a function, because first derivative is the slope of the function. Okay, now let's look at this. If f double prime x naught is positive, okay, then what does it mean? The slope of the curve tend to increase. Okay, so it means the slope of the curve, okay, for instance, yeah, I give you a clear example here. F prime x is positive, and at the same time when you try to find f prime x naught, yeah, double prime x naught is also positive. That means if we have this one, the slope is positive, isn't it? Or the slope is increasing, or the curve is increasing. The rate of change in the slope, in the increasing slope here, is positive or increase. So the slope increase at increasing rate. The slope increase means f prime x naught is positive. The slope increase at increasing rate means the second derivative is positive. Okay, now can we have f prime x naught positive and then at the same time f double prime x naught negative? Okay, of course we can. Okay, f prime x naught is positive. That means the slope is increasing, but at what rate? At decreasing rate. If it is at decreasing rate, so let's say I have this curve. Okay, x is here, y is here. I may have this kind of curve. Can you see? If I pick one point here, then I draw the tangent line, the slope looks like this, isn't it? But if I increase the x further, then the slope is flatter. That means, okay, the slope is increasing at decreasing rate. Okay, so this is for this. Okay, all right. Now, so here we need a graph to understand it even more. Let's say y is on the vertical axis, x is here. So we have function y as a function of x. So let's say we draw it and it looks like this. Let's see. Okay, all right. Now, so here, if we look at this graph, let's say we pick one point here, call it point A. And then if you draw a tangent line that passes through point A, okay, and then you move here, call it point B, and then you draw the tangent line here, you can see that, okay, the slope is increasing but then becomes flatter, isn't it? Okay, so here at point A, we have x1. We move to point B, we have x2. At point A, the slope here is f prime x, which is positive, isn't it? Because you can see from this side, the curve is upsloping. But as we move to point B, okay, the slope becomes flatter, isn't it? Now, for this kind of curve, you can see the shape here is what we call strictly concave. Why? Because along the point here, from here until here, okay, regardless whether the slope is increasing or decreasing, because below B, the slope is increasing. After point B, the slope is decreasing, isn't it? But the curvature of the curve is basically concave. And when it is concave, that means f double prime x is negative. That means this second derivative, like I mentioned to you just now, measures the rate of change of the first derivative. The first derivative at point A is increasing but at decreasing rate. If we pick another point here and then you draw the tangent line point C, the slope is decreasing. Okay, let's call this one x3. Okay, and you know what happens here is that it is, also concave, isn't it? Like a upside down bowl. And f double prime x is negative. Okay. Now, this kind of curve is what we call strictly concave. How to detect that a curve is a strictly concave curve? Based on the drawing. Now, if you draw a straight line and call that straight line of MN, pick one point here, call it M. Pick another point here, the other side, call it N. When you join it, you draw a straight line. Then you can see the line of MN here is below the curve. Then we know that it is strictly concave. Okay, what's the opposite of strictly concave? Obviously, strictly convex, isn't it? Now, how to determine that in the form of graph? Can you do the same like the way I did for strictly concave, but this time it is for strictly convex. Check the first derivative, check the second derivative, and make sure you know how to explain it. So here, what does it mean by f double prime x, or second derivative? It actually shows the curvature of the curve itself, okay? Whether it is convex, concave, or straight line. Okay, so recall back the second derivative here, okay? It could be equals to 0, less than 0, or greater than 0. Now, if the second derivative is equal to 0, okay, so what does it mean? You already know that if it is less than 0, that means it is concave. If it is more than 0, that means it is convex, isn't it? But what does it mean if it is equals to 0? Okay, then it means at that particular point, okay, the slope of the curve is actually flat, isn't it? Okay, now there are some terms that you must know. Okay, concave, strictly concave, convex, strictly convex. But what's the difference between convex and strictly convex? Then we are looking at the conditions for each of the above type of curves. So here, let's say f double prime of x is less than 0. Okay, like I said earlier, the curve must be concave, isn't it? And it is concave for all x in y. Okay, then if f double prime x is less than 0 for all x in y, we call it strictly concave. The opposite is convex. Okay, so correction here, f double prime. Okay, so here you can check the statement using this function. So if you take the first derivative, f prime x, isn't it? Then it becomes 4x cubed. Okay. Now, if you take the second derivative, then it becomes 12x squared. Now, for this, for x cubed, okay, the first derivative, because the power of x is 3, and x can be any number, okay, can be negative or positive. So f prime x can be upsloping or downsloping. That means this one can be greater than 0, less than 0, or equal to 0, isn't it? Okay, but if you look at the second derivative here, you put any number x, be it negative or positive, what happens to the y double prime x here? It's gonna be positive all the time. Why? Because x squared, regardless whether x is negative or positive, x squared becomes positive, isn't it? Multiplied by 12, it's also positive. So that means second derivative for this function is positive. If it is positive, then it means the curve is convex, isn't it? Now, so if the curve is convex, is it convex or strictly convex? Okay. How do you check it? It is very obvious that for all x here, okay, when you square it, it becomes positive. So y double prime is always positive for all x, isn't it? Then it is very clear that it is strictly convex. Okay. Now, let's look at the application of the second derivative here. What I want you to do is, from this expression 1 here, check the concavity of 1 when the value of a, the coefficient here, yeah, the parameter here, is positive. And then you change the value of a becomes negative. Check the concavity. When we say you need to check the concavity, it means you need to check the f double prime x or y double prime. Okay, and we know that b is between 0 and 1. So given these two information 1 and information 2, check the concavity of expression 1. Next, we're going to look at the economic application of second derivative. There are a lot of economic application of second derivative, but this time we're going to look at the attitude towards risk. The attitude toward risk, different people has different attitude toward risk. I'm sure you have heard these terms: risk averse, risk lover. Okay, so some people are risk averse, some people are risk lover, but majority of them are risk averse. But some people are in the middle; they're just neutral or indifferent. Okay, now how to analyze different type of people in terms of their attitude towards risk. So here we can use concavity and also convexity concepts that we already learned just now for the above objective. So let's crack on. So let's say we have an individual who have 15 pound and utilize this whole 15 pound for a betting game. So he expect to win the game, but he observed that there are two different payoffs. Okay, so we have two different payoff here. If he throws a die and an odd number shows up, he will get 10 quid. But if he throws a die and an even number shows up, he will earn 20. Okay, so let it be 50% for each of the outcome. Why? Because for a die, we have 6 sides and we have 3 odd numbers. We also have 3 even numbers. So that's why it becomes 50-50 for each type of number, odd number and even number. Then the expected value of payoff for him in this case would be 0.5 times 10 if he throws a die and an odd number shows, plus 0.5 times 20 if he throws a die and an even number shows up. Okay, so altogether expected value that he may earn is 15 quid. Can we consider the game is fair? All right, when the payoff received here in terms of expected value is 15 and the cost is 15. Yes, because the payoff is equal to the cost. But do you think that this game still has a risk? And if you say yes, what is the risk here? All right. So, of course, there's still risk in this game. All right, because we are not so sure whether he can get 10 or 20. But we know that the probability is 50% for each of them. Okay, so that means, the actual results of this individual, is unknown. So when the results is unknown, so the game still has a risk. Okay, so that's why some people are very skeptical about this game, especially who are risk averse. But those people who are not skeptical but want to play the game without any hesitation, then we call them as risk lover. Okay, now, but how to explain these two opposite behavior, risk averse and risk lover, using mathematics, in particular using concavity and also convexity concept here. So we can try to look at concavity concept and risk averse attitude first. Okay, so here use this graph. So we have measurement of utility of good X, where X is the payoff of playing the game. Okay, so X is the payoff in terms of dollar here. All right, and then we have this concave curve. So this is the utility of a person who is risk averse. Okay, so now let's say what we want to do here is we want to show you in terms of concavity, how we can explain this concept of risk averse using concavity function. All right, now, so what we have here is strictly concave utility function for risk averse individual given by ux, such that, so we have ux such that u0 equal to 0, because if we don't play game, we don't get utility from this game, isn't it? Also, ux is positive. That means, recall back, x is the payoff in terms of dollar. When you play the game, the higher the payoff, the higher utility you get. So utility curve is upsloping like what is shown here. And because of its concavity, then you have we have to have u prime x is positive. That means it's upsloping. Okay, so that means marginal utility of playing the game is positive. However, u double prime x is negative. Okay, that means if this one is marginal utility, which is positive, This one shows that marginal utility is diminishing as we increase the number of payoff. Okay, for all x. That's what it means. Okay, now for this game, the individual has economic decision that he has to make. So there are two options. Okay, number one, if not playing the game, okay, then he saved the cost because the cost of playing the game is $15 or 15 quid, yeah, 15 quid. Okay, 15 quid. Now, so from here, he received 15 quid. So the utility of having 15 quid is this. Okay, utility of 15. And in the graph, we can put it, let's say here, call it at point A. Okay, point A is here. And then we have the amount of money or payoff for not, spending cost is 15. So the utility is here, U15. And it is very certain because you don't involve any risk at all. Okay, now, so the height for this case is A, this much, yeah. So I don't want to miss the graph. I just show you in the form of pointer here, from here to here, the height. Okay, the height is A. Okay, now, but if the individual playing the game, okay, then there are two possibilities. Okay, so play the game. Two possibility. The first one, okay, 50% he will receive payoff of 10. Okay, 0.5, 10 pound payoff if play the game. Okay, and then here it is shown at point M, for instance. Let's say M is here. Okay, so this is M. And then receive 10. The utility 10 is here. And then you receive $10 here. Or 10 pound. This is pound. The second, possibility of playing game is 50% he will receive 20. Okay, 50% he will receive 20. And then that is shown by, let's say, point N here. Okay, so let's say 20 is here, then utility is here, yeah. Okay, now, so because it involves probability, then we are not certain about the outcome or the payoff. Okay, but then we know the expected value or the expected payoff from playing the game because we can either receive 10 or 20 quid for this individual. Now, so expected utility here, okay, is given by what? 0.5 times 10 plus 0.5 times 20, and this gives us 15 quid. Okay, this gives us 15 quid. However, the next question is, where is the expected utility when you play the game? Why do we call it expected utility? Because the payoff 15 here is uncertain, isn't it? Because we have probability here. So whatever utility we receive from this particular 15 is what we call expected utility. But where is the expected utility? When we play the game. Okay? The expected utility when we play the game is the average height of M and N. Okay? So the height of M is this. If we are so certain that we get 10 quid, our utility is 10. We don't call it expected utility. If we are so certain that we receive 20, our utility will be 20 here. I don't want to mess the graph. However, because when we play the game, it involves probability of getting either 10 or 20, then we calculate expected utility. Now, the expected utility of 15 is here. The expected utility of 15, okay, is actually the average height of M and N. So this is M, the height of M. This is the height of N, okay? So it must be halfway. So when you draw a line that connects M and N, you draw a line that connects M and N, then the line here hits 15 here, isn't it? So this is the height. This is the height, or call it average height of M and N. And call this particular point, let's say point B. So the value here is expected utility of 15, isn't it? Can you see clearly the height of A is bigger than the height of B? And thus, the utility of getting 15, without playing is higher than the expected utility when you play. Okay, you can see clearly because this one is higher than this. Okay, so point B here is the average height of point M and N. Okay, now, as you can see here, when the expected utility is lower, then we could understand why for those risk-averse people, they have lower tendency to play the game compared to, the, risk lover. Why? Because if it is certain, everybody will go for it. But if it is uncertain, then you can say the expected utility is lower than the actual utility. And we are uncertain in terms of income because of the expected utility value here is lower. Okay, the height is lower. Okay, but what about if the person is, risk lover? So we have the frame of diagram here. Can you try it on your own and then compare with the results in the textbook? You'll see the difference. Because in the risk averse example here, utility is higher than expected utility. You could expect that for, for the risk lover, okay, utility will be higher than the expected utility. Okay, so here, can you see the line MN? Okay, this one. MN is drawn below the curve. Okay, so for any concave curve, the straight line that passes through two different points will always lie below the curve, isn't it? Like I said earlier. Okay, so from here, what is straight concavity? The straight line that, that connects the 2 points along the curve, from the curve, must be below. Then you know it is straight concave. Okay, curve. Now, can you also see that the expected utility of playing the game is lower than utility of the cost of the game itself? Because the cost of the game is 15, isn't it? Okay. Now, so we can see from here, the game should be avoided then. Okay. So try for the, convexity for risk level and see the differences. Now, we move to the second derivative test. The second derivative test, okay, can help us to check whether, we have relative maximum or relative minimum. So the second order derivative is used to check whether we have relative maximum or relative minimum. Okay, so here we must understand that we must do the first order condition. Okay, check whether the first order we differentiate it first and then check whether the first order condition exists or not. Okay, then let's say I gave you this graph. This is for simplification. So x is here, fx is here. then let's say it looks like this for simplicity. Let's say at the maximum point here is x naught. Okay, so you must check at f prime x naught, yeah, at the value of x naught. When you check the slope there, it must be 0, regardless what happens to the left or what happens to the right. So when the slope is flat, let me fix the drawing. When the slope is flat, then we can see that, okay, the tangent line at x naught is flat as well. Okay, so the tangent line slope is 0. Okay, but that's not sufficient. That's just give indication that there is a relative extremum exists, but we don't know whether it is maximum or minimum. That's why we need to do the second derivative test, okay, at x naught. So in the graph, if we are given the graph, then we know that it is maximum point, okay. But how do we know it is a maximum point when the graph is not given? Okay, how do we know at x naught we have maximum point? So a relative maximum exists if second derivative value at x naught here is negative. Okay, so what you need to do is f prime double prime x naught, you take it and then you check the value whether it's negative or positive or equal to 0. So if it is negative like this at this particular point, that you know that it is you know the maximum point. Okay, but it will be the other way around if you know the f double prime x naught is greater than 0. But what happens if, to the curve if f double prime x naught is 0? Okay, then we don't know whether it is having maximum or minimum point. Okay, then we have this kind of critical point could be called as inflection point. Have you heard about this before? Alright, but anyway, find the relative extremum for the following. Check whether it is maximum point or not at particular x naught. So for instance, let's say you look at question 1, y equal to 3x squared minus x. You need to find f prime x first. Then we have 6x minus 1, isn't it? And then you need to find the first order condition. The first order condition means the f prime x here that you have found equate it to 0. Then this one is first order condition. Now, the first order condition here can give you the value of x equivalent to what? And that value of x, okay, in this case, is actually what? Is actually, you do the calculation, okay, you bring 6x to the left, 1 to the right, okay, then you will get x equivalent to 1, 6, isn't it? 1, 6. Okay, so this is the x naught that we are referring to at this particular point. But now we don't know whether it's maximum or minimum point. So that's why you need to do the second derivative test. Okay, so the second derivative test here, okay, second order condition, f double prime x, okay, equals to 6. So obviously 6 is greater than 0, it is a positive. So obviously it won't be this graph, it will be, the opposite graph. So try to finish it, show the graph and see what happens. Okay, so do the same for question number 2. Now, but from here, what we can see is that, okay, we can have, okay, f double prime x naught can be equal to 0, less than 0 or greater than 0. So which one? What happens if it is less? If it is less, this happens. What happens if it is more? This happens, isn't it? Maximum point relative, maximum exists. Okay, but what happens if it is equal to 0? Like I said just now, you may have heard the term inflection point. Okay, so now we have done FOC, we have done SOC. Okay, so actually when we have FOC, f prime x equal to 0, yeah, this one equals to 0. Okay, that is not sufficient for us to detect whether the graph is having relative maximum or minimum. That's why it leads to the second derivative test. Okay, the second derivative test, okay, can help us in determining whether we have maximum or minimum point. Okay, or we don't have both of them. Now, so f prime x naught is just a necessary condition for the second derivative test. Okay, in order for you to do the second derivative test, you must get the first order condition done first. Okay, so the equation of first order condition, or f prime x equal to 0, is like I said just now, is actually the first order condition, also known as first order condition. And we already know from previous lesson that f prime x equal to 0, okay, when x is at x naught, has a stationary value. So x naught is here, so it is stationary, doesn't change, the slope is flat. Okay, but you know, like I said, the first order condition is just a necessary condition for the second order derivative. Okay, but to make us very sure about whether we have relative maximum or relative minimum, we need to do second derivative test. So the second derivative test becomes the sufficient condition criteria to determine whether we have relative minimum or relative maximum here. So this is what I said just now. So when we have f prime x equals to 0, it leads to the second derivative test, because if we don't do the second derivative test, then we don't know whether it is a relative maximum or relative minimum. So f prime x is just a necessary condition for the second derivative test. Alright, so like I said earlier, it is first order condition. Okay, so the second derivative test is just a matter of deciding whether the stationary value is a relative maximum or minimum. Okay, so when we have the results of second derivative test, f double prime x is greater than 0 or less than 0, these two are basically the sufficient conditions. Alright, so sufficient conditions to determine whether we have relative maximum or relative minimum. Okay, but what happens if we have f prime x equal to 0? Like I said earlier, it could be inflection point. Can you show it in the form of graph? Can you search for this kind of graph? Now, we want to move to the economic applications of first and second order conditions. And actually, there are many examples. Yeah, for instance, conditions for profit maximization, coefficient of a cubic total function, cost function, upward sloping of marginal revenue curve, optimization of utility function that is subject to constraint. Yeah. So, but we have limited time. So we want to look at the first one here, which is condition for profit maximization. Now, if we look at the condition for profit maximization here, we have the profit function in which revenue minus cost. Okay. Now, revenue minus cost is given by expression 4. Now, the first thing that we need to do is to calculate the first order condition, because by having first order condition, we know that the profit has been maximized. Okay, so the first order condition is delta P over delta Q, which is delta R over delta Q minus delta C over delta Q, and equate it to 0. Once you equate it to 0, then only you can call it first order condition. If you don't equate it to 0, it's just a simple partial differentiation. Okay. Now, once you equate it to 0, then you can find a particular Q, call it Q star. Previous example is X naught, isn't it? Now we call it Q star. At that Q star, it could be relative maximum, minimum, or inflection point. At Q star, this point is a stationary point because the slope is flat. Okay. Now, the slope refers to this marginal profit in economic terms. Okay, so we are done with the first order condition. Now next, we need to calculate the second order condition. So for the second order condition, we differentiate the profit function with respect to Q once again. So we get delta 2P, delta Q, and then 2 here. Okay, and then this minus this. Okay, don't equate it to 0 because we just want to find the sign of this, whether it is greater or less or equal to 0. Don't just equate it to 0. We don't know whether it is greater, we don't know whether it is equal, we don't know whether it's less. So we put question mark here. Okay, now, and in this case, if I put it here, if delta, if the second order condition here is like this, okay, which is less than 0, then it means the second derivative is less than 0 or negative, isn't it? That means the curve is concave. Okay, so at particular q star, okay, then we know we have relative maximum because it's logic, yeah. Profit maximization, we must have maximum point. Okay, if it is less, there's something wrong with the calculation because you are maximizing profit. Unless if you talk about cost function, you are minimizing cost, perhaps this one will be, more than 0, and then we have convexity, and then we have minimum point. Okay, now, okay, in the form of graph, we can show it this way. So let's say our revenue function looks like this, yeah, increasing. As we produce more output, revenue increasing, but at decreasing rate. And then let's say for simplicity, our cost function start here because we have fixed cost even if we don't produce. Let's say cost function is here. Let me fix the drawing, otherwise it doesn't look nice. Okay, so let's say here, let's say somewhere here. Okay. Now, let's say we have profit function that look like this. Okay. So this is profit function. Okay. Now, if you look at the maximum point here, okay, you look at my drawing, and then we have something like this. Okay, so I have point, let's say point H here, and then point J here, and then we have maximum point here, and then we call it Q star, Q star. Okay, at point H and point J, the tangent line for at point H is tangent line for revenue function, tangent line for cost function at point J, where quantity is at Q star, and then you can see profit is at its maximum, and then here you have delta P over delta Q equal to 0, isn't it? Okay, and then if you draw a line, it becomes flat like this. Okay, now at this point, delta P over delta Q equal to 0 at Q star. And then we also have, when it is equal to 0, that means delta R over delta Q equals to delta C over delta Q, isn't it? Because marginal profit is equal to marginal revenue minus marginal cost, okay, equal to 0. Okay, not only that, how do we know we have maximized profit here? Because if we take the second order derivative, second order test, yeah, derivative test, this one will be less. That means concave. And then concave looks like this upside down bowl, or it doesn't mean that it's always upside down bowl when we talk about concave, but concave looks like this. Okay, if it is on the left side, if you put tangent line becomes flatter and flatter. If put on the right side, becomes more negative. Okay, that's what it means. Okay, so but then you can try with other types of curve. Let's say cost function here. If you look at the cost function here, okay, you draw cost function like this. Okay, so you have cost, you have quantity, and then you draw marginal cost here, yeah, and then you see the difference. Okay, and then you can find the minimum, the minimum point and whatnot, and then you can check whether it is convex or concave based on the condition that we have seen. So this is the necessary condition. This is the sufficient condition in order to check whether it is relative maximum or minimum. Now, in this case, it is relative maximum because the sufficient condition has been proven, saying that second order derivative test is negative. Okay. We move to the last bit of this chapter. It's called Maclaurin and Taylor series. I'm sure this is very new to you. And so, what are these two series all about, and what are they for? Usually, let's say Maclaurin or Taylor series, it is used to approximate a function locally. Okay, when I say locally, it means, for instance, in economic analysis, economic analysis is done locally or around equilibrium or around steady states. So when we want to analyze equilibrium and steady state, there will be a function that is near to that equilibrium point or steady state, isn't it? So you know that the function in reality is not always linear. Sometimes, curvy on the left side and also um, a straight line on the right side of that equilibrium. So we can use this Maclaurin or Taylor series, okay, to approximate a function that is close to equilibrium or steady states. Perhaps now you cannot appreciate it because you are not using it currently. But when you are, studying at the higher level, let's say masters or also PhD or doing research, then you can appreciate the use of Maclaurin and Taylor series, like the way you appreciate, the concavity and also convexity of a curve when you try to learn the risk averse or risk level case for individual person, when he or she plays any kind of game. Okay, now, so in mathematics, when we talk about Taylor series, it is actually a representation, okay, of a function as an infinite sum, as an infinite sum of terms, okay, that are calculated from the values of a function derivatives. So that's why it is learned in this chapter at a single point. Single point, single value, let's say point x, x naught, a, b, c, or whatever. So Taylor series was formulated by the Scottish mathematicians James Gregory, but only then it was formally introduced by an English man called Taylor in 1715. That's why it's called Taylor series. Now, so if the Taylor series is centered at zero, instead of a certain constant, then that series is called Maclaurin series. So that's why you learn Maclaurin first, then you go to Taylor series. So Maclaurin series was named after the Scottish mathematicians Colin Maclaurin. So he used this extensively for special case of Taylor series in the 18th century. So you can imagine mathematicians during that time was already in studying a very sophisticated terms. Now, both Maclaurin and Taylor series represent the expansion of function f x around zero or a point, let's say point x naught, okay, and then at that point x naught, let's say we have steady state or equilibrium or anything that we want to analyze in economic study. Okay, now, so when we talk about expansion, so the word expansion of the function, any kind of function f x, is actually, okay, expansion, the transformation of the function f x into polynomial form. So you have function f x, okay, you try to transform it into polynomial form in which the coefficient of the various terms are expressed in terms of the derivative values, okay. So we have the coefficient or parameters. All of these are expressed in the derivatives value. Let's say f prime x naught, f double prime x naught, okay, f triple prime x naught, etc. And all of these are evaluated at the expansion point. Let's say point x naught. Okay, so point x naught can be any number, positive, negative, whatever. But if you want to make it zero, then it's called Maclaurin series. Okay, so we want to talk about the simplest thing first. So we look at Maclaurin series first. Okay, so let's consider we have a function, call it fx, and fx here is a polynomial function. So this is the original function, yeah. Okay, so we have original function in 5. What we want to do is that we want to, expand it into an equivalent of nth degree polynomial where we have the coefficient. You look here, these are the coefficient, okay, are expressed in terms of derivative value, okay, f prime 0, f double prime 0, and etc. So how can we do this? Okay, so now please find f prime x. So if we were to find f prime x from original function 5 here, we have a1 plus 2a2x, isn't it? Plus 3a3x squared, isn't it? And then plus 4a4 x cubed, isn't it? Plus until n times a n x to the power of n minus 1, isn't it? So for the second one, we have 2a2, isn't it? Plus 3 times 2 a3x, isn't it? Plus 4 times 3 a4 x square, isn't it? Plus until here n times n minus 1 an, and then we have here x n minus 2, isn't it? Okay, and if we continue until the last one here, okay, then we can have n times n minus 1, isn't it? And then we have it multiplied by n minus 2 multiplied by n minus 3, okay, and then continue multiplying until 3 times 2 times 1 n, isn't it? Okay, can't you see after you do f prime x, f double prime x, f triple prime x until the last one here, can you see we have 1, 2, 3, 4 until these terms, but now for every successive differentiation, the terms reduces to reduces in number by 1, isn't it? Okay, so now you can see a1 gone. In the second one, you only have coefficient 2a2. In the last one, you have one coefficient only, the rest gone. That's what I mean. Okay, so here, if we try to evaluate, okay, at x equivalent to 0, yeah, this particular x value equivalent to 0, okay, then we can have, let me write it here, okay, we can have f prime 0 equals to a1, isn't it? Because x here becomes 0, then we are left with a1. Then we can have f double prime 0 equals to a2, isn't it? Because for the second one here, x becomes 0, then we are left with this coefficient. And so on and so forth. F triple prime 0 equals to 3 times 2, a3, isn't it? So on and so forth. Okay? Now, so for all of this, the one that I have written just now, okay, for all of this, if I adopt a shorthand symbol, let's say n factorial, yeah, if I adopt it, okay, such that where n factorial is actually equivalent to n times n minus 1, n minus 2, until, okay, I don't have enough space here, let me rewrite it again. But I'm sure you know this formula anyway, because you have seen this formula before when you did it in the high school. So I want to transform it, adopt a shorthand instead, a symbol, let's say n factorial, where n factorial is actually what? It's actually n times n minus 1 times n minus 2 until 3 times 2 times 1, yeah? Such that n is a positive integer. It has to be a positive integer. Okay? So all of this, the one that I have, circle somehow emphasize here. F prime 0 equal to A1, F double prime 0 equal to 2A2 here can be written as, as this. So A1, I can write it this way, F prime 0, 1 factorial. Why? Because 0 factorial, because 0 factorial is 1, not 1 factorial. Okay, now, so I can have A2 equals to F double prime 0, 2 factorial, and I can have A3 F double prime 0, 3 factorial, so on so forth until an f n times differentiated 0 n factorial. Okay, so here, okay, so what we have done here is that, okay, so all of this derivative, we have done this because we want to do Maclaurin series here. We have evaluate the derivatives at x not equal to 0, yeah. So what happens next here? Okay, so next, okay, what we need to do is that, okay, we already have all of these. Okay, let's go back to the original function, which is 5. So what you need to do is that you have a1 equal to this, substitute it back into 5 here. So you see a1 here, okay, and then a2, a3, a4 until the end, and then you can get something like in 6. Okay, you have some things like in 6. Okay, so the first one here is coefficient a1, a0, isn't it, and not, and then this is okay, a1, isn't it, so on and so forth. Okay, so expression in 6 is what we call as Maclaurin's formula. Okay, so can you try for this example here? Find the Maclaurin series for the function equals to 2 plus 4x plus 3x square. Let me rewrite again the function so that we can always refer to it here. So fx is given by 2 plus 4x plus 3x squared. So we want to get the Maclaurin series expansions. What we need to do here is that if you go back to the Maclaurin formula, it is given by expression 6, isn't it? So you need to find f prime x naught evaluated at 0, f double prime x naught evaluated at 0 as well, so on and so forth. So what we need to do here is that to first differentiate the primitive function. Okay, first derivative becomes 4 plus 6x, isn't it? And then differentiate it again. As long as we see x here, we differentiate it again. F double prime x equal to 6, isn't it? That's it. We cannot differentiate it anymore. Okay, so let's say here for this, it becomes what? So f prime 0, because Maclaurin we evaluate x equal to 0, yeah. Then 6 times 0 is 0, so it's we are left with 4. So for this one, f double prime 0 is what? It's always a constant 6, isn't it? Therefore, Maclaurin series is given by this. Okay, so fx equal to f0, okay, plus f prime 0 over, not over, not, it can be 1 factorial, but it's just the same, equivalent to 1, so I don't write it here, times x plus f double prime 0 over 2, okay, times x square. If you recall back here, we have 2 factorials. So 2 factorials means 2 times 1 is equivalent to 2, isn't it? So that's why here I don't put 2 factorial. Okay. Alright, now here we know that f evaluated at 0 is 2, because this is f, 0 here, 0 here, 2, 2, isn't it? Plus, what we are doing now is to check whether it is true that Maclaurin series give the original function or not. So I'm doing it now. So for this becomes 4x, yeah, for this. And then for this becomes 3x squared. Okay, for this. You can substitute back all the value here. Okay, so this is Maclaurin expansion actually. But if I try to explain it in detail, let me erase this. Okay, it's actually in between. This one is 2 plus 4x plus 6 over 2 times x squared, isn't it? And then it goes to this. Now, Maclaurin series is this one. Okay, when we want to check whether we have done the right Maclaurin series, we transform it back into the original function, and it so happens that this original function is the same as the one given in the question. So, yes, Maclaurin series does indeed correctly represent the given function, which is this, yeah? Okay. Next, after we look at Maclaurin series, we want to look at Taylor series. So now our x0 has to be non-zero, yeah? Now, because it has to be non-zero, okay, so Taylor series actually is an expansion of a function f(x) around a specific point, a point x0, which is not 0. Alright, so let's say we take any value x, and x is a deviation from x0, okay, and in particular x is equivalent to x0 plus delta. So delta here is basically the deviation. So when it is a deviation, it is a difference between x and x0, isn't it? Okay, so here, can you write the, rewrite the following here when the value is no longer 0? Okay, so can you do the same thing for 2 plus 4x plus 3x squared that we used for Maclaurin series earlier? Okay, so let's say fx is given by this. Okay, if you try to write it is in this form, yeah, so it becomes what? F x equals to 2 plus 4 x0 plus delta, isn't it? Okay, because x now is represented by this, and we have some deviation here which is given by delta, plus 3, okay, we have multiplied by x0 times plus delta square. Okay, so this is for fx. What about f prime x? So if it is f prime x, it becomes 4, isn't it? Plus 6, okay? x0 plus delta. Earlier, we don't have delta. Remember when we did the Maclaurin series? And then f double prime is 6. Okay, so this is for this, this is for this. We cannot differentiate it further because x is no longer there. Okay, now, can you see now? Okay, so x is actually x0 plus delta, isn't it? And it is a variable, okay, in a function. There is a variable in the function. Which one is the variable? Okay, now, you see x0 here is fixed because it is a chosen number, isn't it? It's a specific point. Remember, it is a specific point. So x0 is fixed. x0 is fixed. So particular x here can only increase or decrease if delta increase or decrease, isn't it? Okay, so what we can say here is that delta is a variable, isn't it? And x depends on delta, not x0, isn't it? Therefore, from here, we can say that function f(x) is a function of delta, isn't it? So, let's name it g delta, okay? Now, so that means, okay, recall by f(x) that we have here. Okay, so original function f(x) is this one, isn't it? So this fx here is a function of delta if we allow it to, to have difference in terms of delta. So recall back, we have fx equals to 2 plus 4x plus 3x squared, isn't it? Okay. Now, call this a. So like I said earlier, we say that in the previous slide, fx is a function of delta. So we can write it in another form, gd, isn't it? G delta. So here, because we rename it as g delta, then we can have something like this, isn't it? G delta is actually equivalent to 2, okay, plus 4. X now is substituted by x naught plus delta, isn't it? Because that's what we said earlier. Can 3 times x naught plus delta square. And then this is actually equivalent to fx, isn't it? Okay, recall back, x equal to x naught plus delta, substitute it. So this is actually equivalent to original function as well, isn't it? Primitive function. So when we try to find g prime delta, we can have 4 plus 6 x naught plus delta, isn't it? Okay, which is equivalent to f prime x, isn't it? We can also have the second derivative g double prime delta equivalent to 6, isn't it? Because no longer x we want to differentiate, which is also equals to f double prime x, isn't it? Okay. So if we use this for Maclaurin series case, so in Maclaurin series, all of this, yeah, g prime, g double prime, then we can have something like this. G delta equal to g 0, 0 factorial, isn't it? Plus g prime 0, 1 factorial, isn't it? Times delta plus g double prime 0 over 2 factorial times delta square. Okay. And then we can have something like this. So it continues with something like this. 2 plus 4 plus 6. Sorry. Shouldn't be x naught plus delta. Okay. Over 1 factorial delta plus 0, isn't it? Okay. Now, so but in Maclaurin case here, because delta is equivalent to 0 in x equivalent to x naught plus delta, isn't it? Then it implies x equivalent to x naught, isn't it? Because delta doesn't exist. Okay. Now, because we say earlier, yeah, we say earlier that g delta is actually an identity to fx. Okay. Then we can have something like this. G0 is actually f, okay, x naught, isn't it? Okay. And g prime 0 is actually f prime x naught, isn't it? And then g double prime 0 is actually f double prime x naught. Okay. So if we substitute back all of this, okay, back into this one, back into this, all of this, yeah? Okay, call this one equation 1, call this one equation 2, substitute 2 back into 1, okay? Then we can have something like this. Fx, okay, equal to g delta x equals to fx naught over 0 factorial plus f prime x naught over 1 factorial and then times x minus x naught plus, okay, f double prime x naught over 2 factorials times x minus x naught square plus many terms until the last term f differentiated n times, okay, over n factorial times x minus x naught to the power of n. So what does this mean? Okay, all of this. It is actually an expansion of fx around specific value of x equivalent to x naught. Okay, because as you can see now, the coefficients now involve the derivatives of f prime a x naught, f double prime x naught, f triple prime x naught, okay, etc. at x equivalents to x naught, isn't it? Okay, now here, this is what I said just now. Recall back x equal to x naught plus delta, isn't it? So x naught is a fixed number. What is the variable in this case? Like I said, x can only change if delta increase or decrease, isn't it? So here, what's the implication of this particular variable here to the function of fx? Okay, then we did something like this just now. Gx is identical to fx, isn't it? Alright, so this is what we did just now. So how do we rewrite g delta? Okay, I did mention to you it is written this way in equation 1, isn't it? Okay, now, so next find the derivative of g prime delta and g double prime delta. We did it already here. Okay, g prime delta is this, g double prime delta is this, if we are given the specific one. Okay, but if it is written in Maclaurin series, it is equation 1 here. Okay, and then we rewrite it again, that looks like this. Okay, now why it is only up to g double prime delta? Because in the question given specifically to us, we cannot differentiate it further because g double prime delta is 6. You don't see x anymore. Okay, now, okay, this time we don't have delta equivalent to 0 and we don't have x equivalent to x naught. Why? Because x naught is no longer 0. So from here, we can write Taylor series. Okay, so Taylor series that we have written looks like this in general form. Now, if we have a specific function, so let's say we use this fx equal to 2 plus 4x plus 3x squared. Okay, so here, if we write it in the form of x naught, fx naught equals to 2 plus 4x naught plus 3x naught square, isn't it? If we take the first derivative, it becomes f prime x naught equals to 4 plus 6x naught, isn't it? If we take the second derivative, it will be 6, isn't it? So the Taylor's polynomial should look like this. Fx naught equals to 2, okay, plus 4x naught plus 3x naught square, the original function, divided by 0 factorial plus the first derivative, which is 4 plus 6x naught, okay, divided by 1 factorial times the deviation x minus x naught, okay, and then plus the last one, which is, okay, 6 divided by 2 factorial times x minus x naught square, okay. Now, because, x naught is actually the specific value of x, okay, then we can rewrite this polynomial function like this because we just want to check whether we have done the correct things or not. Okay, so it becomes 2 plus 4x naught plus 3x naught square. Okay, and then like I said earlier, since it's x naught is equivalent to x, we can have something like that. Have x equivalent to 2 plus 4x plus 3x square. This one is the polynomial expansion, yeah, all of this. But what I did for the last two here is just to check whether, okay, it's just to verify that the Taylor polynomials does correctly represent the given function, the primitive function. Okay, so you try to do exercise here, A and P, yeah? Try to find the Taylor series and also the Maclaurin series for both of them. And in fact, you can find a lot of exercises from the textbook and also the internet, yeah. But be careful with the notation. In the textbook, we use x naught. When you try to find some exercises from the internet, instead of using x naught, they use a. Okay, so these are interchangeably giving you the same meaning. So try all of them, and then try to understand the concept. You can also see a lot of explanation from the YouTube about Taylor series and also Maclaurin series, but make sure you try to find the one that is related to mathematical economics because most of them are for Bachelor of Mathematics and also Bachelor of Engineering. Okay, so that's all